You can also preset it if you want, but
What, to record when you wanted to?
yeah, I mean, when I teach at Simon's Rock
Yeah, that's
with
nice.
remote classes, I preset the default to be record.
Oh, I see. I thought you could enter in a delay. It'd be nice if you could say start recording in a few minutes or something.
Oh, no, that, I wish I could because, or something, because at times it gets to be or you can pause and restart.
So are your students actually listening in?
Oh, yeah. It actually worked. I mean, in person is better. But
Bruce wanted me to tell a funny story. I was it you or Steiner that was on a Navy barge being towed by a sub, and the sub went underwater, and you had to cut it with an axe? Is that you? Or was that Steiner?
Yeah, it's a question directed to me, Ed Friedman. Now, it's a story I heard from my colleagues when we were out in the middle of the ocean doing acoustic testing of submarines, and they say, oh yeah, we almost got killed because the submarine had its orders to go over there a couple of miles and descend 300 feet and then come back under the boat that had the sensors, and the submarine dive planes caught the cable that held all the hydrophones dangling down into the ocean. And these cables are like this big. They're probably, well, they would have turned the barge over.
Okay, but that wasn't you. You didn't do that.
I didn't, but my colleagues were on a barge that was in that situation, and they knew they had minutes to sever the cable. So they had axes and they found a chainsaw, which is not something you normally find on a boat. And they cut the cable because they would have been killed. Or at least,
Okay, at least my memory is still good.
No, your memory is not
story,
good.
not a Steiner.
Don't pat yourself on the back. Your memory's not good. You're an old. How do we say this? You're an old fart, and so I can't tell you how many things you've forgotten because you would.
Crowd.
Never mind. I can't.
Same with you.
Oh, you got a
Same with
little
you.
bandwidth
We
issue.
agree on something and then you bring it back up a week later.
Yeah, like an old pizza. I would bring it back up.
Well, I've heard about the senility prayer, and again, let me remember this and forget those that I'd like to forget or something. I don't.
All right, so if we're waiting, I have a joke about senility. So this jogger is in the park and he's running and he runs past a bench and there's an old man sitting on the bench weeping. So the runner stops and he says to the old man, can I help? And the old man is just inconsolable. He's just weeping and weeping. And finally he calms down. And so some conversation ensues. Well, what's the problem? He said, well, my wife died years ago and I was very lonely. So I got in touch with one of these agencies that connected with me with a young woman who lived in Russia. And I paid for her to come to the United States. And we met, and it was, she was 30 years younger than me. And there was fantastic chemistry between us. And ultimately we got married. And the runner says, well, that sounds pretty good. He said, well, it was a dream because she was a fantastic cook and the sex was fantastic and she was smart and funny. And I said, well, why are you crying? He said, I don't remember where I live. See, he didn't know how to get home.
Shall we start?
Yeah, let's start.
Oh, more jokes.
Okay.
I don't think we need an introduction because
Yes, we do.
well, yeah, we can
Yeah.
do. There may be some.
Well, do you keep it short?
Let me give a little introduction for you,
Go
Ed.
ahead.
And then everybody else, mute your speakers and I'll mute mine as soon as I'm done. So only Ed is talking. He's a retired rocket scientist. I'm reading from our last book. with space telescope experience. Oh, that's you doing that, Ed. Okay.
Yeah.
He holds a BS in physics from the University of Maryland and PhD from Wayne State University. His career is focused on space-based optical systems for monitoring Earth's climate and weather, laser comm, ocean science, planet detection, astrophysics, defense, and intelligence systems. Since retiring, he's become a regular consultant to NASA, concentrating on evaluating proposals for space science missions. He has worked at MITRE, Martin Marietta in Denver, which is where we met in '85, and also Boeing and Ball Aerospace, and was a adjunct professor at the University of Colorado. Ed, all yours. I'll mute mine.
Greetings and thanks for attending. Luckily, I set an alarm this morning for this talk because I would have missed this presentation, except that the alarm started beeping. I'm going to talk about some bizarre mathematics tonight. And so I hope you will be patient. I've tried to include evidence that this bizarre mathematics is actually true and is endorsed by Mother Nature, pictured here on my first slide. For example, I'm going to show you that this is true, that the sum of all the natural numbers, 1, 2, 3, and so forth, is a negative number less than 1. And I'm going to show you evidence that Mother Nature approves of this result. So, like I say, please bear with me. If you have questions, we'll address them along the way, unless I can detect that the question is going to take more time than the flow of the lecture allows, and then I will defer the answer to the end. So let's start with some basic stuff. Well, first of all, I want to talk about some surprising but not astounding results from odd mathematics, and we'll kind of dip our foot into the water slowly. We'll talk about the properties of circles in different geometries, imaginary numbers, the calculus of residues, and then we'll get into some actual physical proof that Mother Nature approves of these odd results that I'm going to show you. The Casimir effect, which involves something called the Riemann zeta function, which we'll get to. We'll talk about divergent sums that are used in string theory and quantum electrodynamics, here abbreviated QED. So let's start with the thing we all learned in the, 7th grade, that the circumference of a circle is 2 pi r, but that's not always true. Now, so here's a plane, and we're going to see this plane again in about 40 minutes, but let me just confirm with you that for a plane, the shortest distance between 2 points is a straight line. Triangles have 180 degrees. Parallel lines remain parallel forever. And the circumference of a circle is 2 pi r. But that is not true. None of that is true on a sphere. And the reason I mentioned spheres is the topic of cosmology addresses the possible geometry of our universe. We'll be talking about that some more later. And on a sphere, the circumference of a circle is less than 2 pi r. So if you measure the radius of a circle, let's say we have a circle here on the plane, a 1 meter radius. If we measure off a 1 meter distance on the surface of a sphere and also measure the circumference of that circle, the circumference is less than 2 pi r. This is not common knowledge. And if we're dealing with a hyperbola, which is another possible shape for the universe, the opposite is true. The circumference is greater than 2 pi r. Furthermore, on the sphere, parallel lines that are parallel anywhere, for example, great circles that are parallel at the equator, they in fact do touch. They touch at the pole. And similar kind of oddities occur concerning how many degrees there are. In fact, I think I have, yes, So on a plane, a triangle has 180 degrees. On a sphere, a triangle can be as much as 540 degrees. And on a hyperbola, a triangle has less than 180 degrees. So as I say, we're just dipping our toe into the exotic math world. We're going to be completely submerged in a couple of minutes.
Simple question. So when I fly to China from New York, is that why I go over the north, either the North Pole?
Well, there's a couple of reasons. The shortest distance between any 2 points on a sphere is a great circle. Moreover, no planes fly directly across the Pacific. For example, if you were flying from Tokyo, draw a great circle that goes to Santiago, Chile, for example. They don't do that. They fly, they have segments where they can get to a landing point. So the longest trip right now is Perth to Calcutta, or Mumbai to Perth. That's a route that just got approved about 3 years ago for a 2-engine airplane. So the 777 actually makes that flight. It's like 11 hours. You're just out there. If something bad happens, you're a goner. Okay, back to the math. So here's another strange thing, and that's imaginary numbers. We all encountered this in perhaps in the 9th or 10th grade, solving quadratic equations. And we've all seen this. And for those of us who work or have worked in the engineering, math, or physics world, we know that the imaginary numbers are critical to getting answers about the way the world functions and how to design things and so forth. But we have to remind ourselves that the square root of -1 is not real. Literally, it's not real in a mathematical sense, and it's not real in a physical sense. You will never see the letter I, meaning the square root of -1, in the design, the final design of a piece of equipment or a scientific experiment. Even in quantum mechanics, which desperately depends on the square root of -1, any computation that pertains to the real world, such as the probability that an electron is here or there or somewhere else, all those I's are gone because the results of the calculation has to be real in two senses. It has to be real numbers, and it has to be real in the world in which we live in. So this is something where most of you have familiarity with this concept, but we have to remind ourselves this is unexpected. And the history of it goes back to the middle of the 1500s. But we're going to see this again, well, actually in the next page. In fact, there are numerous applications for extended dimensions of imaginary numbers into the world of what are called quaternions, which are used regularly in the design of spaceflight navigation systems. Ultimately, everything that is done by the designer or the scientist ends up as real numbers, but the way to get the answer can depend on multidimensional imaginary numbers. So, and there's plenty of information out there about quaternions if that's something you're interested in. So here are a few weird things about complex numbers. This first equation, Euler's equation, considered the most beautiful equation ever created, says that e to the I pi plus 1 equals 0. And it's considered beautiful because it includes the natural logarithm number, e, the square root of -1, I, pi, 1, and 0, all in a single equation. And even though I is not real, there are many bizarre properties it has. For example, if you raise I, which is not real, to the ith power, which is mind-bending, the result of that calculation is a real number. And I've included a proof of that in the appendix. So I should remind everybody, or say for the first time, reminding myself, there's an appendix to this presentation. And if you see this little box down here with an asterisk, it means there's more information on this topic in the appendix. And you can always write to me and I can talk with you about these results. What's even more bizarre about I to the I is there are an infinite number of real numbers that satisfy this equation. This is the largest of them. And there's, as I say, there's a proof in the appendix of how you get there. Here's another weird thing. If you take the natural log of 2i, which is an imaginary number, you get, the result is complex. But the logarithm of I is imaginary. That, what I mean to say here when I say complex, is a combination of real and imaginary, but the logarithm of I is purely imaginary, has no real part. So there's an endless array of research dating back, as I say, to the middle 1500s on properties of complex numbers, but they are absolutely essential to the mathematics we use to do virtually everything in our world, and yet they are not real. And this is something we tend to forget about when we get, when we're doing a problem, we just slinging eyes everywhere and forgetting they all have to get resolved at the end of the problem, or you have not, you don't have something that's useful.
So yeah,
Yes.
is there a simple closed form of I to the I?
Yes, so I recommend you go look at the solution in the appendix.
Okay.
And or, once you look at that, if it doesn't make sense, let me know and I can send you a, I don't know, 15-page lecture that I've done on that topic. Okay, the number line, we all learned this probably in the 4th grade or earlier. These are real numbers ranging in this example from -6 to +7. And we tend to organize our thinking about all the numbers we deal with in the real world as have a presence on the number line. Nothing strange there. Now let's consider this function, 1/1 + x squared. And here's a graph of 1/1 + x squared for negative and positive numbers. And a typical calculus class, you would learn how to calculate the area under this curve from -infinity to infinity. And let me just make sure everybody understands I use the term function, and in a simple way, we just say this is some kind of a mathematical machine that converts one number into another. So like the sine function is a good example of a function. So if you've never seen functions before, that's what we're talking about. We change the input value, the output value changes in some self-consistent way. For example, here's the sine function. The input values are on the number line that goes, in this case, from -3 pi to +3 pi. And the sine function gives us this oscillating output. So let's go back to our example of calculating the area under the curve 1/1 + x squared. And there's a number of ways to do this in your calculus class, and we get a result. The answer turns out to be pi. And most of you did this problem back in your teen years. But as we get deeper into the mathematics ocean, we have to introduce Bernard Riemann, who died in the middle 1800s. He said, I would like to modify the number line in a way I'll show you on the next page. Here's Bernard Riemann. He only lived 40 years, but he made some amazing discoveries in the field of what's called complex analysis. He said the number line is inadequate to explain the range of numbers that we work with in mathematics and related sciences. So in this case, we have the real axis and we have an imaginary axis. And you can, any point in here has both a real and imaginary component. I could talk for an hour about how you interpret what's going on this plane, sometimes called an Argand diagram. But I want to point out that the equation that we talked about, 1 over 1 plus x squared, does not exist at 2 points on this complex in this complex plane, because at the point I, which has no real part, it only has an imaginary part equal to I. If we square this function says square a number, so if we take I and square it, we get -1. And 1 over 1 minus 1 is 1 over 0, and that's undefined. When I was a kid, we were taught that's infinity. We have to be a little more subtle about it. The function does not exist at this point. It exists everywhere else in the plane, except it does not exist at this point either, a minus I, because if I square minus I, the square of 2 negatives is a positive, and I have I squared, which is also -1. And once again, the function does not exist at either of the points I've highlighted with these black dots. Now, what Riemann said is, I'm interested in solving the problem of the area under this function, which we did on the previous page, and we got pi. And he invented a category of mathematics called contour integration, which turns any integral into an algebra problem. It's extraordinarily powerful. So once again, our function exists everywhere except where the 2 dots are, because we're dividing by 0. Riemann found that he could derive the area of the curve on the prior page by ignoring this point. You have to ignore it in the right way. You ignore this point and do some algebra, and you get the same answer. You get pi. Or alternatively, you can ignore this point and you get the right answer. When the first time I saw this, I was shocked and amazed. Now, this is a trivial example, but Riemann invented an incredibly powerful sledgehammer, and this function is analyzed using his technique called contour integration, swatting a fly with a sledgehammer, but very sophisticated problems can be solved using his technique. It requires going to the imaginary, including the imaginary axis. So we have the real number line, and we also have the imaginary number line. And when you venture into that part of the mathematics ocean, you end up with an extremely powerful methodology for doing very complex, literally complex problems. So this, I want to re-emphasize what Riemann did. He exploited properties of non-real numbers, namely these 2 points, at locations where the function that we're evaluating does not exist, and invented a method for looking at the point where the function does not exist and getting the area under the curve of the function when real numbers are injected into the function. This is an extraordinary result. So what he invented, as I said, calculus of residues. There's more to this that we're going to be talking about. So at this point, I want to reflect on the fact that the most powerful tool we have when we do problems in engineering and the physical sciences is mathematics. We don't yet know if mathematics has full capability to describe the universe we live in. There are fields of mathematics, such as string theory, which we will talk about later, where the mathematics is so involved and complex. Sorry, I don't want to use that word 2 ways. So complicated that solutions are not within reach. These are problems where instead of a world of 3 dimensions, we have a world of 500 dimensions, maybe more. But I just want to take a little pause here to remind us that the world that we are trying to describe with mathematics is certainly not fully explored yet, And a good example of this, the accidental synergy that has occurred in developing solutions to physics problems is Einstein's theory of general relativity, which he invented between, say, 1905 and 1917. And it depended immensely. No progress would have occurred except that Einstein's friend Grossman was an expert on a topic that had no practical application at the time, the topic of differential geometry, which was invented by our friend Riemann and later by a French mathematician, Cauchy. So the Cauchy-Riemann development of differential geometry, which was completed in the 1880s, had it not existed, Einstein would have made no practical progress on the theory of relativity. Now I'm talking about his theory of gravity. But Einstein knew somebody who was an expert on a useless thing called differential geometry, and out of that we get practical applications every one of us owns, namely the GPS that's in your cell phone, which GPS does not work unless you know how to manipulate Einstein's theory of relativity and deal with the fact that clocks run at different rates on satellites and the surface of Earth. Can all of science be described by mathematics? There's no inherent reason to believe this is true. There may be branches of, say, the physical sciences where we cannot make progress unless we invent another tool that complements what we know about mathematics, because math is derived from logic and self-consistent manipulation of numbers and equations. Mother Nature has nothing to do with that enterprise. And yet math is absolutely essential for our progress in the physical sciences. Furthermore, we don't know if the theories that have been developed, such as the theory of relativity and quantum mechanics and all this other stuff, we don't know if those theories are unique. There's no way to know if the solutions that we have created or will create are the only ways to deal with the way nature functions. So let's keep those things in mind. So let's do some examples of exotic math. Now we're going to get submerged in the math ocean. So the Casimir effect, I'll explain the history of it in a minute, but it all depends on creating a box, probably in outer space, and putting nothing in the box. If anything is in the box, let's say there are a few hydrogen atoms, we're going to take those out. So the box is completely empty. We're going to chill the walls of the box to as close to absolute zero as we can get, so that there's no black body radiation emanating from the walls of the box. That's something those of you who have taken physics will know about black body radiation. So we have an entirely empty box. And Casimir in late 1940s, 1948, speculated that the interior of this box is not empty, that Heisenberg's uncertainty principle says that particles of all kinds can emerge and disappear as long as they satisfy Heisenberg's uncertainty principle. That is, a highly energetic particle can exist for an extremely short time, and then it must disappear back into the vacuum. And so the concept of a vacuum these days, and starting in the late 40s, actually in the mid 30s, but really refined in the late 40s, the concept of an empty space is it's not empty at all. It's full of a churning foam of particles and light of all types and all wavelengths, and it's just filled with surging activity. Most of the activity occurs in a way that's undetectable, but Casimir speculated that he had a way to detect this surging foam in the empty box by doing this experiment. He imagined we take our empty box and we put two conducting plates in the box, And we put these two plates as close together as we dare. And he conjectures, for reasons I will explain in a minute, that you would detect a force between these two plates, that the two plates would be driven together. And here's why. The box, the empty box, is filled with these virtual particles. In this case, I'm just going to talk about light particles called photons. The box is filled with these virtual photons flying around and disappearing. And the space between the plates, if we make it small enough, that will exclude some of the light that is spontaneously appearing and disappearing in the empty box, because the wavelength has to fit between these two conducting plates. These are like boundary conditions for what can live in this space. So he said, the box is filled with all wavelengths, but between the plates, some of the wavelengths are excluded because their wavelength is too long, and those light particles just won't fit. So this line just says what I just said. There will be a difference in the density of light particles, virtual particles, between the plates and outside the plates in the empty box. Everybody thought he was nuts. There's a little footnote about virtual particles. I explained that verbally. Everybody thought he was crazy. Turned out he wasn't crazy. So here's a drawing. Again, imagine we have a big box. All kinds of wavelengths are churning around everywhere, except the waves that fit between the two planes, these two plates, have to fit like strings on a guitar. They have to fit because these are conducting plates. So you can have this frequency can exist, or this wavelength, and this wavelength is twice that, and so forth. But there's an infinite number of shorter wavelengths that can fit in here. So outside the plates, in this space here, all wavelengths are allowed, limited only by the size of the box. But in this space, the longest wavelength allowed is the one illustrated right here. So there's a difference between the energy density here and the energy density between the plates. Hence, there's a force driving the plates together. And using new techniques that had just emerged in the 1940s, Casimir did a calculation of the energy density outside and inside the plate area. And he found that outside, in the box, but not between the plates, all frequencies consistent with the size of the box were allowed, and that if you add those all up, you get infinity. He also calculated the energy density between the plates, and all frequencies above this one are allowed, and you also get infinity because there's an infinite number of shorter and shorter wavelengths that can fit in this space. So we now have two infinities, but they're not the same because outside the box, outside the plates, longer wavelengths are allowed that are not allowed in here. So we have now an interesting math problem that deals with the difference between two infinities. And that's a measure of the force between the plates. So we have this. We have an infinity outside the plates, but inside the box. And we have the infinity between the plates, but they're not the same scale of infinity. And as I said, Casimir used the techniques that were emerging in dealing with problems like this, and he did the arithmetic I'm going to show you, and he got this, that the difference of the two infinities is a number 1 over 120, which is interesting. You can imagine an arithmetic that says infinity equals infinity plus 120. That's not offensive. But anyway, he did the calculation. And by the way, the details of his calculation are in the appendix. And doing the calculation in a way that gave us the difference of the infinities requires Casimir to use something called Riemann's zeta function. This is the Greek letter zeta. and it's easy to describe. It's an infinite sum of terms. Here's the definition of the zeta function. So like other functions, we have some input. Here we call s. And in our case, s is an integer. So any number we put into the zeta function is described by this summation. For those who haven't seen this before, this says, for every value of n between 1 and infinity, add up the terms defined this way. And here they are. 1 over 1 to the s, 1 over 2 to the s, 1 over 3, and so forth, an infinite sum. So we put in some number for s and plug it in every term in the sum. And that's the way Casimir dealt with the difference of the infinities. It's a well understood function. It's been studied since the 1850s. And to get his result, he had to evaluate the zeta function for the integer -3. And so zeta, if you look at a table of mathematics, you will find the zeta function with a input of -3 gives you 1 over 120, just what what Casimir found. Here's a picture of the zeta function. It's quite beautiful. There's still some unanswered questions about a detail related to the zeta function, but nonetheless, Casimir did his calculation, evaluated zeta of -3, got a result 120. As I say, this is described in a lot of detail in the appendix. And 50 years after his 1948 presentation on this topic, measurements were finally made of the Casimir effect. It requires that the plates, here are the plate separations, the plate separation has to be measured on a scale of hundreds of nanometers. And the plates have to be of extraordinary quality, flatness, smoothness, and so forth. And people actually in 1998 made the measurement, and here's their data, the little data points. And the black curve is Casimir's calculation. And the data and the theory match. Mother Nature has put her stamp of approval on his theory. By the way, it's very interesting, and I've included it, that you can get almost the right answer without doing any physics using dimensional analysis. I've included that in the appendix. It turns out that the force experienced by the plates goes as the 4th power of the separation. But to get the actual numerical result, you have to do Casimir's theory. So Mother Nature approves of this. So hallelujah, theory works. Casimir's reputation has been restored. The many famous physicists who thought he was nuts now look like they're too timid. But we're not done with this. So let's go to the next page. Remember, I told you that Casimir had to use this result. And I also told you that the zeta function is defined this way. Let's see what it looks like if we put a -3 in everywhere there's an s. We get the sum of the cubes, an infinite sum of cubes, which is equal to 1 over 120. This is the first, or perhaps the second, very surprising result we find, and I want to emphasize, Riemann's zeta function depends on leaving the number line of real numbers and going into the complex plane we saw a few minutes ago, and doing an evaluation and then coming back into the real world, and we find these kinds of results, that the sum of the cubes is equal to 1 over 120, which seems nonsensical because every term is the cube. These are getting larger and larger rapidly. And under normal circumstances, we would say that this sum is divergent. That is, it sums to infinity. But by exploiting the complex plane to do the evaluation and then coming back from that mysterious territory into our our real world, we get this kind of result. And this is one of many I'm going to show you that are like this. So obviously something odd's going on. The sum of, by the way, these are all positive numbers, all larger than 1, or equal to or larger than 1, yields a result that's smaller than 1. But we already saw Mother Nature put her stamp of approval on the theory, which depends on this result. So we should not be too quick to reject this result, since we have a powerful force in our world, Mother Nature, saying this has been certified true. And it's not the only case. The way Casimir did his work used something called renormalization, which is a technique which for other problems was invented in the late 40s and resulted in a Nobel Prize I'm going to tell you about. So the Casimir experiment is one of many examples of how to manipulate infinities when we do physics problems. And the world of renormalization is a large and growing world that is required for a number of kinds of problems, including problems as what you might consider as mundane as studying how crystals remain stable. If you do the theories of solids in detail using quantum mechanics, infinities occur everywhere, but it is possible to avoid the infinities and get real practical results, one of which I will show you. But to do that, you have to be willing to swallow this result that, oh, didn't want to go there. You have to be able to accommodate this kind of crazy result, that the sum, a divergent sum, is equal to a number less than 1. So let us keep going. So essentially, what Casimir found, as I illustrated earlier, the difference between the infinity between the plates and the infinity outside the plates was different by the number 1 over 120. And if I had written this down initially, you would have had no problem with this, because for any infinite number, I can add some other number and I still have an infinity. In fact, I could add a negative number to infinity and I would still have an infinity. This is sometimes called, this piece here is sometimes called a nugget. And the zeta function gives us access, and it's not the only one that gives us access to the nugget. There's a paper by Dowling, which I list here, does the Casimir effect 2 ways. He does one for particles of light, photons, which are massless, and gets the right answer. And then he redoes the calculation if he allows particles with mass to be in the box. Remember, I said the box is empty, but the foam, the quantum mechanical foam allowed by Heisenberg's uncertainty principle, can include electrons, protons, all sorts of stuff. So if you're technically interested, you might want to take a look at Dowling's work, where he does the Casimir effect 2 different ways, manipulating the infinities, and he gets the right answer both times. So let's look at an example of renormalization. If you did not take calculus in your education or career, you could maybe go get a coffee or a beer. So let's look at a simple problem. This says, I would like to know the difference between these 2 integrals, 1 over z dz from 0 to a, and the same thing from 0 to b. And this integral always leads to a logarithm. So I have the logarithm of a, this, minus the logarithm of b, this, and then 2 terms, logarithm, both logarithm of 0 here. And you'll remember that the logarithm is not defined for a value of 0. But we can get a sensible answer from this by using a very simple form of renormalization. Also, you'll find the word regularization. If you look in Wikipedia or something, that also will lead to some information about this. So how do we get rid of these logarithms of 0, which are not defined in all of mathematics? So here's how we do it. Instead of putting zeros here, we put some small number epsilon, like epsilon sub A and epsilon sub B, and do the problem, and we get this result, very similar to this result, except we have a logarithm of epsilon A and epsilon B, and we cannot let either one of these go to zero, or we end up with this problem. But if we rewrite the function like this, the logarithm of a difference, log A minus log B is equal to the log of that ratio of A over B, and the log of these two epsilons, it appears in the same way. Now, as long as we drive epsilon A and epsilon B to zero so that this ratio is always equal to 1, we get the right answer. This is a simple form of renormalization. We just insist, sorry for that little flag that pops up. We insist that as we drive epsilon to zero, the ratio of the epsilon A to epsilon B has always got to be equal to 1. Say it another way. Epsilon A and epsilon B always have to have the same value as they go to zero. And then we get the right answer, which is the difference between these two integrals is log of A over B, which is fine. So that's an example of how, a very trivial example of how physicists and mathematicians deal with renormalization. So now let's go to another topic. Quantum electrodynamics also emerged in the 30s incompletely. The work was interrupted by World War II, and after the war, 3 giants of physics emerged. I'll tell you who they are in a second. And they attacked the problem of the magnetic properties of the electron. So let me check the clock and make sure I got about 15 to 17 minutes left. Here's the problem, a challenging problem with the magnetic properties of the electron. Electron has electric charge. It also exhibits something we call spin. The electron itself is not spinning, but it can be described in a simple way as the rotation of the electric field of the electron. This was discovered in the early 1930s. Electrons have spin. A spinning electric field generates a magnetic field. The magnetic field interacts with the electric field generated by the electron. So the electron is surrounded by interacting electric and magnetic fields of its own creation, and it is embedded in the center of this field of fields. What's more, because the electron has charge, when virtual particles appear spontaneously in the vacuum around an isolated electron, the positive charge items that spontaneously appear are drawn toward the electron because the electron has a negative charge and positive charges want to get married to negative charges. So the electron, just by standing there, is so attractive that it induces a cloud of positive charges to form around it. So if you're standing a little bit away from the electron, you see an electron surrounded by some positive charge, which reduces the effective charge that you witness or feel if you are a charged particle. That polarization of what's called polarization of the vacuum changes the electric and magnetic fields that electron generated in the first place. And if you try to do the arithmetic associated with this process, you end up with an infinite sum of terms that you have to add up if you want to calculate the magnetic properties of the electron. An important thing happened in the late 40s based on the technology of World War II, namely microwave technology. People were able to measure the magnetic properties of electrons with incredible precision, which I will illustrate to you in a second. When they did this, they got a number different than the trivial result you get if you ignore all these self-interactions that electrons have with the electric and magnetic fields that they produce. There's a difference between what we measure and the theory that existed, say, in 1945. That difference had to do with the electron interacting with the fields that it produces. So the three giants I mentioned, Schwinger, an American, Richard Feynman, many of you have heard of him, and Tominaga, a Japanese, all worked on this problem from as early as 1942. Tominaga, who was hiding out trying to avoid being bombed to death in Japan, he was working on this problem. Schwinger was in New York, and Feynman was all over the place in the Manhattan Project. And anyway, by 1948, they independently came up with a calculation of the magnetic property of the electron that matched experiment. This is called the anomalous magnetic moment of the electron. All three got the same answer, and all three were confronted with the problem of infinities involving the interactions of the electric and magnetic fields that the electron induces in itself and its polarization of the vacuum that is around the electron, the polarization of virtual particles appearing around the electron. Infinities everywhere in the theory, but the quantum electrodynamics turns out is luckily, one of the theories that is renormalizable. Not all theories are. And so by working through techniques such as Casimir did, and the trivial example I gave you on the prior page, they got around the infinities and they all got the same answer. Ultimately, Friedman Dyson, someone many of you might have encountered, died just recently. He was the only one who understood all three theories because the languages were very different. But Dyson was able to show the three theories were equivalent, even though these people worked independently. They won the Nobel Prize for this work in 1965, I think. And since then, it's been another 50 years, more work has been done. The model stands up, little changes have been made. Here's the difference between the calculation that you get avoiding the infinities, you get this number. The uncertainty is out here in the third decimal, these parentheses. And here's the measurement. So, and it matters, the zero matters. So we have 4, 5, 6, 7, 8, 9, 10, 11, 12 digits that match between the theory and the experiment. We get a little change here. The calculation says 16 and the measurement says 7. But this is the most accurate computation ever achieved in science. And it depends on getting rid of infinities all over the place in the calculations. And as I say, 3 different people did the calculation 3 different ways. They all got these numbers. These are the modern numbers, by the way, because the experiments have gotten better too. When the Nobel Prize was awarded, the match was good to, I think, right here. But it now is good for another digit, and it's pretty good. But it all depended on getting rid of infinity. So let me just tell you why I told you this story. Avoiding the infinities requires schematic techniques. And here are some quotes from people who were central to the development of the theory, who were very dissatisfied with the throwing away the infinities in clever ways. Paul Dirac, Nobel Prize winner. Feynman, Nobel Prize winner, thought that renormalization is not legitimate. Dirac, this Nobel Prize winner, told Feynman, it's an ugly theory, we got to do it again. And yet, we know it works. And in fact, Nobel Prize winner Weinberg says, has to be more or less correct. Maybe we're just not describing it in the right way, which gets to my point a half an hour ago about, are the theories we have about the real world unique? Perhaps someday people will redo the theory using a different approach and not have to deal with infinities. And so there's a couple of links you can go to. Let's go to string theory, which is a relatively new theory for the description of subatomic particles. It has been in the mainstream and out of the mainstream of physics. It involves some incredibly difficult math. its predictions that could be confirmed in experiment are very difficult to achieve because it describes the smallest elements of subatomic particles, the pieces that make neutrons, protons, and electrons. And so getting to that level requires a brand of physics we haven't invented yet, that is physics experiments. It also depends on the zeta function, and it depends on this result. Zeta of -1, which Riemann showed us is equal to -1/12. And once again, here's the definition of the zeta function. It's an infinite series. And if we put in -1, where there's an S here, so everywhere here, we're going to put in a -1, what do we get? We get, this is, once again, this is the definition of the zeta function. S is -1, we get this. That zeta of -1 is equal to 1 + 2 + 3 + 4, infinite. And I just showed you that that's equal to -1/12. This is the equation I showed you on the first page, on the cover page of this talk. That the sum of the natural numbers, when evaluated by going into the complex plane and doing the proper mathematics there, and then coming back to the real world, you get this result. If you go on the internet, if you go on YouTube, you'll find, I don't know, 500 people arguing about how is this possibly true? Well, the answer is controversial, but Mother Nature has given us, sorry, I gotta go back, apologize, has given us this result, that manipulations of the type I just showed you match the measurements made with a very precise microwave technique, and it's the best theory ever invented by humans. So once again, Mother Nature has put her hand on our shoulder and said, this sum is true. Not only, this is the first time we've seen that the sum of an infinite series is not only a number smaller than 1, like the sum of the cubes is equal to 1/120, it's a negative number. And string theory exploits this. This is for one of the pages from Polchinski's seminal book on string theory from 2005, and he points out right there that we have to exploit this odd, he calls it an odd result, that the sum of the natural numbers is equal to -1/12. So I thought I'd show you how you can calculate this in a simple way that you can show to your kids or grandkids. Let's take a sum A, which is the alternating sum 1 - 1 + 1 - 1, blah, blah, blah. And we'll just put a parenthesis here, which means we can factor out a minus sign, and we have 1 minus this thing here. But this is what we started with. This in the parens is this. So what we've written is that A equals 1 minus A. So the alternating sum 1 - 1 + 1 is equal to 1/2. This doesn't seem too crazy, right? If you take an infinite series of 1s and -1s and add them up, well, maybe the average is 1/2. Now let's do some more arithmetic. Let's define a sum C equal to 1 + 2 + 3 and so forth. And then we'll multiply C times 4, which 4 times 1 is 4. And we're going to put that 4 here. And 2 times 4 is 8, and we'll put that 8 here. And 3 times 4 is 12, put that here. Now what we're going to do is subtract this row from this row. So we get -3C is equal to 1 - 2 + 3 - 4 + 5 . So we get this alternating series. What do we do with that? So it turns out, this is a well-known result. Those who have taken calculus will recognize this, that when you expand this function, which is almost the one we did earlier in this lecture, not quite the same, you get this. You get 1 - 2x + 3x squared with the and this has been proven thousands and millions of times. We know this is true, but let's let x equal 1. So 1 over 1 plus 1 squared is 1/4, because we have a 2 down here, which is squared. And when we put 1s in this, we get 1 minus 2 plus 3 minus 4 plus 5 minus 6, which is what we have here. So we now know that minus 3c is equal to 1/4. So c, we divide through by minus 3, c equals minus 1/12. So this is a trivial way to show this kind of result. And this creates all kind of howling and upset on YouTube. Nonetheless, I don't want to have to go back again, but the results from quantum electrodynamics for the anomalous magnetic moment of the electron rely on calculations like this. So we should not poke Mother Nature in the eye. Here are some additional results. We've already seen 2 of them. The zeta function for an argument of -1 is equal to -1/12. We also saw this, 1/20. These are other results we have not looked at, but there they are. And I'll remind you that -1/12 is equal to the sum of the natural numbers. 120, 1 over 120 is equal to the sum of the cubes of the natural numbers. -1 over 252 is equal to the sum of the 5th powers of the natural numbers, and so forth. It also turns out that if you put in even numbers, notice all these numbers I've put in here are odd. If you put in even numbers, you always get a 0. Now let me show you a particularly odd graphical result. First, I'm going to lead you in another direction for a second. If we take the sum of the inverse squares, 1 over 1 squared, 2 squared, 3 squared, and so forth, it's well known that sum is equal to pi squared over 6. So you might wonder, how is it that this sum, which involves, these are rational fractions. This is 1 over 1, this is 1 over 4, this is 1 over 9. What's that got to do with pi, which is an irrational number? This problem was solved, well, you see the reference in the lower left corner. It's called the Basel problem. It was solved by Euler, a very elaborate calculation in the 1750s, I think. Riemann also attacked this problem using his technique of wandering into the complex plane and manipulating numbers there, and he gets this result in about 3 lines. That's one of the powers of his technique. You can do problems in minutes that would take days and days, or you have to be a genius like Leonhard Euler to do the problem at all. Anyway, it gave us a little breather to wonder, why is it that rational numbers are related to pi? Okay, now let's look at the zeta function for the argument -1. Here's a sum that most of us saw this maybe in high school algebra, that if you sum the digits, not to infinity, but up to n, the sum is equal to n times n plus 1 over 2. Carl Friedrich Gauss solved that as a 10-year-old. There's a famous story about that, where his the class he was in was being unruly, and the teacher of the class of 10-year-olds said, "I'm going to punish you. I want you to add all the numbers between 1 and 100." And Gauss did the problem in about 2 minutes by noticing that 1 plus 100 is 101, and 2 plus 99 is 101, and 3 plus 98 is 101, and you add those up and you multiply by 50, which is the middle of this, which is half of n. That's where this 2 comes from. And you get the answer. The answer is 5050. Now, if we convert this summation into an integral, well, first, here's the graph of this sum. If we turn it into a smooth function, and then I zoomed in on this part right down here because I want you to be able to see this detail. If we turn this into an integral that looks like this, notice it's built like this. N times n plus 1 over 2, I now have x times x plus 1 over 2, and I integrate that. Is there an interesting range of integration that gives me something interesting to talk about? And the answer is, if I integrate from -1 to 0, I get the area of this little gully, and the answer comes out to be -1/12. Now remember, I started this by beginning the process of adding the natural numbers. In a sense, by doing this integration, I've explored this for this little span between -1 and 0, and I get the result you get if you sum this to infinity, -1/12. If we do it for the sum of cubes, here's a formula for the sum of cubes. If we do the same thing, take this, turn it into a variable, blah, 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 everything here is here, and integrate it from -1 to 0, that's this, you get +120, just like the Riemann zeta function. How about if we do it for the sum of the fifth powers? This is as far as I went. Here's the equation for a non-infinite sum of fifth powers. So when you pick n to be some number, 10 or 3 or something, and then do this arithmetic and you will get the sum. Turn that into an integral, integrate from -1 to 0. You get -1/52, which is the area here, and is equal to what Riemann's zeta function gives if you put in a -5. There it is. Why this is true is not clear to me. I'm continuing to evaluate this problem. I just want to point out a couple of more things and then we'll wrap this up. If you have questions, we can answer questions. I want to emphasize another strange thing about math. Shape is not geometry. I do a lecture series for adults who are interested in cosmology, and I emphasize this. This is a flat geometry. Remember this? I showed you this the very first thing we talked about. Parallel lines never cross, triangles 180, circumference is 2 pi r. In fact, people who do sewing will recognize this as some kind of a thing you can buy, parallel lines that are parallel and at right angles and so forth. But look at what happens if I roll that up into a cylinder. It's a curved shape. Clearly, this rolled up version of this flat thing, this is not flat in the general use of the term, but what's not flat is the shape. It's still a flat geometry. If you look at the lines on this cylinder, parallel lines never cross, triangles have 180 degrees, and circles have a circumference of 2 pi r. So this is an important concept for those who are reading about or taking lectures on cosmology, because it deals with a conceptual challenge that everybody faces, including me, in describing the geometry of the universe we live in. We now know the universe that we live in has a flat geometry, but that does not dictate its shape. And there are many arguments about what the shape of the universe is. Some argument that the universe has the shape of a torus. That involves bending this cylinder so that the ends meet, but that tends to violate these rules. So anyway, I just wanted to alert you, if you get confused about what's described to you about the shape of the universe, make sure you grasp a hold of the difference between shape and geometry. Here are the other two possible shapes for the universe, hyperbolic and spherical, and these rules do not apply in those universes. Here are references.
This is John. I thought that was solved several years ago, a few years ago. The universe is flat.
The universe has a flat geometry.
Yeah.
It does not necessarily have a flat shape. There's a difference, as I illustrate here. So yes, the cosmic microwave background tells us very emphatically, along with other things, that our universe is flat. We think we know why. That'd be another talk I can give. But that does not dictate the shape. So let me just say, there's some further links for those who are interested. And then there's all this gibberish here of backups. So at this point, I'm going to stop and see if people have questions.
Ed, this is John. I have another observation and a question. Both of you zeta functions, one had 12 in the denominator, the other had a 120. And a
Yes.
lot of the others, not all, but several of the others had a number that was evenly divisible by 12 in the denominator. Is there any insight or reason why that would occur?
I can't, yeah, let's go to this page. I don't know. They're also divisible by 2 and maybe 6.
Right, but the first, but a lot of
in
most of them are divisible by 12, all but 1 or 2 are divisible.
You know what, John, what occurs, I hadn't thought about this, good question. 12 is divisible by 2, 3, 4, and 6. That is to say, it's divisible by even numbers smaller than this number. Or powers of 2. Well, obviously, powers of 2 are involved. We got them right here. So, yeah, I don't know. No, I don't know. But thanks for that observation. Something else that will confuse me.
My 252 is, right, it's divisible by all those smaller numbers, but it's also divisible by 12.
Yeah,
And so is 240. You know, a lot of these are.
yeah. But 120 is not, 252 is not divisible by 120.
Some of
Right,
them
well-
are not.
Okay, I'm going to give John an assignment.
32,760 is, but you're right. Some of
John Miller now has an assignment to work that out and give me some advice. Okay, other questions? Or did I?
don't ask a question or you'll get an assignment.
I know, I'm cautious. I've got a kind of a question comment. Well, first of all, really thanks. Well, it shows to me how creative mathematics can be, right? And I think I didn't appreciate that. And the results are completely counterintuitive that I'm going to share with everybody else to annoy them. But anyway, going back to, you started with, was it Riemann who did those,
Yeah,
who showed
Riemann.
that, Riemann, who did you showed that there was an integral and it came to, it was equal to pi or something, right? And you
Right.
did 1500s or something. So my question is, you know, if I got my dates right, this was long before calculus was developed.
Oh, no, wait, well, I'm sorry to interrupt you.
Okay.
Riemann, here's his birth and death dates.
Okay.
The,
All right.
the
So when was-
1500s is when the first arithmetic with complex numbers was done. Addition, subtraction, and multiplication. That was in the 1500s. Riemann was very familiar with calculus.
Okay. That seemed like a contradiction to me. All right. Thanks for clearing that.
Okay. Other comments, questions? No?
Bruce, you're muted if you're talking, Bruce.
Go ahead.
I have a question.
Yes, sir.
You can go.
When you showed the geometry on the plane, on the sphere, and on
Yes,
the
sir.
hyperboloid, I can easily see why the circumference of the circle on the sphere is less than 2 pi r, because r is a curved line. But the same thing's true on the hyperboloid, and I don't understand why it's not
Yeah.
the same as on the sphere.
Well, it isn't, because the shape of the hyperboloid surface is, things are getting farther apart as you move from one point in any direction. The linear distance is getting bigger. The distance on the surface is getting bigger than the projected distance. So if you project, let's make this bigger and I can illustrate what I mean. If you take this and say, I'm going to move from this point to this point, project that line onto a plane and measure this distance. But on the surface, because the surface is like a saddle, the distance on that, along the surface, that distance is bigger than the projected distance. That's why that's true. On a sphere, just the opposite happens.
Yeah, but the hyperboloid,
Well, you know,
is not the same in all directions.
That's true.
It curves one way, in the other direction it curves the other way.
Yeah, that's true. But in general, the general result for hyperbolic surfaces is the circumference is bigger than the 2 pi r. And in fact, this is a technique for determining if you are near a massive object, because a massive object distorts space-time in a spherical way. So if you're near a black hole and you measure a linear distance near you and then measure the circumference, you will find that this pertains, and you can say goodbye to your friends because you're very close to being sucked into a black hole. So
we are wearing masks because we've been exposed to the virus.
Yeah.
Supposed to be staying away from each other.
Well, thank you for wearing the mask. It'll protect all of us who are on this call.
Right. He's actually been in another room on the computer, but
All right. Well, don't remember the old Police song, "Don't Stand So Close to Me," which was about another topic completely. So I'm glad you're doing the right thing.
I have one comment to make.
Yes, sir.
You mentioned that this nonlinear geometry is crucial with the GPS.
Yes.
GPS. But GPS also has linear components as well, doesn't it?
Oh, yeah. So if you go through the calculation of the correction factor for clocks, there's multiple things to take into account. There's the pace at which a clock progresses here on Earth, but there also is a factor associated with Earth's rotational velocity.
Okay.
So there's two terms there, gravitational and motion. Then you go to the satellites that are at 10,000 kilometer altitude and do the same calculation for the clocks on the satellite. And there is a general relativity correction because of the gravity at the point of the satellite is not the same as it is on Earth. And the velocity of the satellites is not the same as the velocity of Earth. So there's actually 4 competing terms that almost cancel out, and the final result you get is you have to run the clocks on the satellite at a rate of 35 nanoseconds per second. You have to take into account that difference between clock rates on Earth and at the satellite is 35 nanoseconds per second. If you don't make that correction, errors would accumulate to about 7 kilometers per day. So you could set your navigation technology when you're at home, because you know where your house is. And by the end of the day, like if you're looking for the nearest 7-Eleven and you don't know where it is and you use your electronics, it would be in a circle 7 kilometers.
So it is an estimate, but a really, really micro estimate. In other words, if a GPS says that you're so many feet, so many blocks from a location, it's going down to the minuscule, like feet.
Centimeters.
Yeah. But it still is an estimate, right?
Oh, yeah. And the reason it's an estimate is the signals from the satellite have to propagate through the ionosphere of Earth, through the atmosphere. So that the ionosphere is the thing that changes most day to night and so forth. So there are dynamic effects that are going on all the time in the way that GPS calculates what it's doing. The example is, I'll give you one that I really like, is farmers these days use GPS to level fields. So they have GPS, and you can see this if you see pictures of modern equipment that farmers use to grade a field. You'll see out on the ends of the plow 2 things that look like GPS stuff. It's a little thing that looks like a big mushroom. They have located GPS receivers and transmitters at the perimeter of the field, and those locations are fixed. When they're driving around, they use something called interferometric GPS. and they can measure the height of the terrain on a scale of a few centimeters, and the plow automatically, the blade of the plow goes up and down, so that when you drive across the field, it makes the field conform to the curvature of Earth, a perfected Earth. Imagine that Earth is an absolute sphere.
I wish my father could have seen that.
Yeah, it's really extraordinary. So when you'll see this when they're creating a new road. They program, like if the road has to go uphill, they program the general terrain slope, and they use interferometric GPS, and they get accuracies on a scale of centimeters.
I want to live forever.
Yeah, it just keeps getting better.
Getting better.
Hey, Ed, can you stop sharing? We could get everybody on screen here.
Oh, yeah. Yeah, there you go.
Yeah, just want to see who's here.
A great talk.
Listen, everybody, hey, thank you tonight for muting yourselves between, because some of your computers make a little noise, and Ed had a nice clean presentation tonight. I didn't have to do so much work.
Great. Yes, I appreciate everybody being diligent about muting.
Great presentation.
Yeah.
Thank you so much.
Yeah, that was good.
Excellent.
That was great. Jared watched it too. He actually wants to email you some questions at some point.
Oh yeah, fantastic. So he can go through Bruce, or maybe already has my email embedded in messages for this group. Yeah, I'm eager to talk about this topic. And
are these talks recorded, Bruce? So can I see if I missed one?
This one is recorded. Most of them are. Some of the early ones weren't, but most of them are.
There's one or two I missed. I can find them pretty easy, I guess, if I go.
Yeah.
Through this, okay.
By the way, next week we're going to hear about Ixemic. I don't know if he's still on, but Mark Ketter, who presented once before, Cochrane's fight, I think he called it. This one's going to be on heart attacks and stress, and he's written probably 100 papers on that subject, so he knows what he's talking about.
Is it next week or the first week in January, Bruce?
Yeah, that's right. First week in January, January 6th, I think.
Yeah.
So that's the election of the Georgia, maybe.
Yeah. There's no homework for this holiday, except for John.
and for Miller.
Yeah.
Yeah.
Thanks again, Ed. Thank
Hey,
you.
thanks everybody for participating and thoughtful questions.
Pretty impressive.
Pretty impressive. You've got a broad knowledge there, my friend.
Yeah.
That's
well, I got more, if we have some gaps in the schedule.
Okay. Well, we may have, we also have someone who's going to be doing how drugs are introduced. He spent his entire career working in New Jersey for one of the big drug companies, and he knows how it's done. Probably a lot of palms getting greased along the way, and I don't really know, but
Hey, Ed,
interesting.
Ed, could you possibly do something? An amazing event that just recently happened was that asteroid. When we landed a craft on an asteroid and it brought it back to Earth. How do you do that? It's just so unbelievable.
Well, here's the way I start that conversation is if you're on an asteroid, don't jump too hard, because the escape velocity for a rock the size of, let's say, the island of Manhattan is, 10 feet per, or 10, let's do metric, 10 meters per second or less. You just got to give a little push and so that's one of the things they exploit. This is the Japanese who did this work, captured a sample and brought it back. You might have seen where it hit the ground. This is landing. The hard part is landing, because you have to have fine control of your thrusts so that when you're landing, your landing velocity has to be less than the escape velocity or you'll bounce off the surface. Mm-hmm. And remember that old game, which was a moon landing thing that you could play, you could use your fuel wisely. If you come in too fast, of course, you're destroyed, you hit the surface. If you come in too slow, you run out of fuel before you land, and the gravity grabs you and crashes you. So landing on a small pebble, and the thing they landed on is,
I know.
I don't know. It's probably smaller than
A couple miles.
couple miles. Yeah, so smaller than the island of Manhattan. The escape velocity is very low. It's not the first time it's been done. This is one of the rare times when we get a sample back. And yeah, it's quite an achievement. The other thing you should know, and this is something I could talk about in a separate talk, is to get to the asteroid, you don't want to have to carry too much fuel. So they exploit what's called the planetary superhighway, which takes advantage of the interaction of the gravitational fields of all the major bodies in the solar system: Sun, Jupiter, Saturn, kind of in that order. And if you go to the right place and go the right direction and give a little puff here and there, you can ride the wave to a destination. You have to be, suddenly the topic of reliability becomes important, because it takes a long time to do this. But you can give a bigger payload to the object of your desire, because you don't have to carry big rockets. You carry little rockets that go puff, puff. And this is an invention that came to people's minds. Actually, the Japanese pioneered this by accident. People were studying trajectories to go to small bodies out near Mars. And a couple of young orbit analysis guys discovered, hey, if we went, instead of going directly at the object, if we go around the moon and just drift away from the moon slowly, we'll encounter that object. And we won't have to use very much fuel at all. And then the math guys got involved, and they applied the method of, or the branch of mathematics called manifolds. And they were able to do the calculations for these exotic trajectories in minutes. The first people to design trajectories this way took days and days or weeks of experiments. But once the math people got involved, they could tell you, okay, we fly to this point, slow down, and just wait. And then the moon or Earth or Saturn or something will move past us and give us a little tug, and we will end up at our destination. We just have to have a reliable spacecraft. And we've had the United States has used this technique to bring back samples of solar wind with, unfortunately, there were some problems with the design. They installed some parts backwards, and the payload hit the ground going very fast here on Earth. It hit the right spot in the desert in Utah, but the accelerometers that were to deploy the parachutes were installed backwards. So the spacecraft was slowing down in the atmosphere, but the parachutes never deployed, and the thing hit the ground going terminal velocity for that shape. And got some science, but the point is they use this technique of the superhighway to navigate to a distant body without having to haul a whole bunch of fuel, which requires a lot of metal to contain the fuel, and big rockets, and the impact of changing from one technique to another is huge. So you can take more stuff, or you can have a smaller mission that's cheaper and get you there. You just have to, the spacecraft has to be alive when it gets there. But anyway, big achievement.
Let's do that talk, Ed. I'm looking forward to that one.
Yeah,
this one kind of, this was great, but it was sort of like, it's amazing, but it's a little hard.
It is hard.
Hard for the grandchildren to follow.
Well, here's the thing. It's hard for the professionals to follow too, because they have gotten to the point now, like I showed you those quotes, where they say, yeah, the theory that we developed works, but it's just so offensive. We're hoping for something better in the future, but if you want to start a fight in a bar, you could take that page where I showed you how to manipulate the infinities and get the -1/12, just adding and subtracting numbers. And there's 100 ways to do it. That's not the only way to get that result. but it matches what Riemann gets by wandering into the complex plane, and it matches what Mother Nature says. That's what impresses me.
Yeah.
Thank you.
Okay, well, thanks, everybody. And January 6th, I believe, whatever Wednesday is nearest to January 6th is when we're going to be having our next talk. And I'm going to see what I can do to find some more talkers. And Ed, you may hear from me.
Bruce, is your group growing and the class is growing, isn't it?
Well, you know, it expands and contracts. Last week, I don't know whether Scott recruited all of his girlfriends or something, but we had a lot of people. Last week we had 34.
Recruiting.
Yeah, Ed's previous talk, or I think actually John Miller's was very well attended, and one of Ed's was very well attended. It depends. I think it depends an awful lot on what's on
Christmas
TV, you know,
Yeah,
and what the holidays are and that sort of thing.
Well, and the topic, you know, I didn't want to dilute the abstract of this talk to make it sound like we're just going to have fun. It's a challenging topic, and maybe that's deflected.
I think it's okay. You're right to do.
No, it was great.
Yeah, that was excellent.
Yeah.
Thank you
I
for
have a
that.
master's degree in mechanical engineering, and I've seen all that math before, but not applied the way that you applied it. So, you know, I don't have a PhD, and these other guys all have PhDs.
Well, neither did Freeman Dyson. Freeman Dyson was the only person on planet Earth who knew that the three guys who won the Nobel Prize all did the same thing and in different ways. He never got a master's degree. I mean, a PhD.
That's great gossip. I didn't know that.
Yeah.
Thanks again.
I met him once. By the way, I met him once. I was at a scientific event, and his wife, who looked like a tiny bird, just skin and bone, very efficient. Her body shape was tiny and compact. And she came up to me and said, I don't know you and you don't know my husband. I'm going to go get him. And she came back with Freeman Dyson.
Wow.
Who, while he shook hands with me, you could tell he was wishing he was somewhere else. He was also small and bird-like.
Yeah.
Bruce, I tell everybody I know to see these talks. I want the word to get around. This is nationwide. What you're doing is nationwide. We can have 40,000 physicists.
Yeah, we could.
International. We need
40,000
somebody.
Yes. Think about how many of us there are.
Yeah.
If you let word of mouth go work, we'll have so many people that'll be competing to give talks.
Well, then there's your homework, everybody.
Well, right, but do we want it?
Forward this to all your physics friends and science loving friends.
I'm serious. If you tell your friends, they will come and see it. Enough of them, and it'll get to be quite big.
Yeah, I'm seeing the effect of this, by the way. In middle of January, I'm starting my lecture series on modern cosmology through the University of Denver. And the last time I taught there, I had 21, you were in a classroom, we had 21 students. I have, I think, something like 40 students now, and they're from all over the United States.
Cool.
Go to this.
Yeah.
It's a little scary.
Yep. You got Oregon, Connecticut, New York,
Colorado.
Yeah.
Which reminds me, I'm repeating my continuing studies course on AI, starting February 10th, 5 weeks. Bruce, maybe I'll send you the link. This one will be
do that.
This one will be in the evenings. Dagmar came to the last
everybody,
one.
and it was great. So did Dagmar.
That was a great class. That was a great class. I really can recommend it.
Yep. Okay.
A bit scary, I have to say.
Good night, everybody.
Hey.
Good night. Thank you.
Night. Thank you.
Night.
Happy New Year, everyone.
Happy
Happy
holidays.
Merry Christmas.
Merry Christmas.
Merry Christmas.
Merry Christmas.